So we're talking about crystalline solids here. Crystalline solids can be divided into three different groups. Molecular solids, the components are molecules. Ionic solids, the components are ions. And atomic solids, the components are atoms. Right? So examples here. So ice. Ice is a solid form of water. It's water molecules arranged in a regular repeating pattern. It's a crystalline solid. It's made up of molecules. It's a molecular solid. What holds those molecules together? Hydrogen bonds for this one, yeah. So intermolecular forces. Intermolecular forces are much weaker than chemical bonds, right? So this is going to melt fairly easily because it's not held so strongly in the solid form. In an ionic solid, something like table salt. So here the particles are sodium ions and chloride ions. What are they held together by? Ionic bonds, right? So that's a much stronger bond between those things. And so ionic solids tend to have high melting points because you have to get them really, really hot. You can melt sodium chloride, but it's over 1,000 degrees, really hot. So these are the largest two groups. Atomic solids, we can divide that into three groups. Non-bonding. Here, the atoms are just held together by dispersion forces, and really the only examples of that are the noble gases. So noble gas atoms just held together by dispersion forces, and those have crazy low melting points. Then we can have metallic solids. These are the most common of the atomic solids. So the atoms are held together by metallic bonds, right? Metals will easily lose an electron or two, and so they can lose an electron or two, and those electrons can just kind of form a pool around these atoms and collectively hold them together. The melting point of metals is variable. Typically when we think of metal, we think of like steel, which is an alloy, or iron. You know, have you ever seen an iron nail melt, even in the heat of summer? No, of course not. But then there's mercury, which is a liquid at room temperature. And gallium, which is a solid at room temperature, but you put it in your hand and it will melt into a liquid. The third is network covalent. So here we have atoms, but they're held together by covalent bonds. So essentially what these solids are is one ginormous molecule. All the parts of it, all the atoms here, are held together by covalent bonds. So when we talk about a formula for it, we're just going to do like we do for the ionic solids and look at the lowest whole number ratio. Those are going to have high melting points. An example there is quartz. Yeah?
So I don't get what's the difference between, so that's SiO2, and then it's H2O, so aren't they?
That's an excellent question. How are those different? Let's see if I can find a picture. Wait, this one here. Metallic. Okay, I'm going to spare the YouTube people. So I already talked about these things, so we're going to go through this quickly. But again, molecular solids are composed of molecules. Example would be ice or dry ice, solid CO2, held together by intermolecular forces. Some molecular solids can crystallize in different structures depending on how they crystallize. And an interesting example of this is chocolate. The different structures are called polymorphs, and it has to do with how hot it was and how quickly it cooled down and froze, became a solid, right? So there are actually 6 different polymorphs of cocoa butter, main ingredient in chocolate. So this looks like a nice piece of really dark chocolate, right? And this one looks a little suspicious. Have you ever opened a candy bar and it looks like that? It's got weird white spots on it, and you're like, is that mold? What's going on there? No, you can go ahead and eat that. The texture might be a little different, but it's still just chocolate. This is a different arrangement of the molecules in the chocolate. And so this is a summary of how the different features are. So this polymorph 5, which has a melting point of 33.8 Celsius, this is the firm, it's got a good snap, it's smooth and shiny, it melts in your mouth, it's most desirable. It's probably not going to melt quickly in your hand, right? So that white stuff is called bloom. And so these other polymorphs have some blooming on them. These guys will melt in your hand. This is what you probably get from that old candy bar. This has some blooming, and you can't form it from a melt. It takes several months to form. So that Halloween chocolate that you forgot in the corner of the cupboard, and you come, next July and you find it, you open it up and it looks like that. It's perfectly fine to eat. I said so, okay? Ionic solids, again, the units are ions. We're going to talk about that more in a minute. The non-bonding solids, okay, the atomic solids, the composite units are atoms. So there's 3 different types. There's the non-bonding. So the only examples of the non-bonding atomic solids are the noble gases in their solid form. And we have the metallic solids. Here's the illustration of the electron C. So these are metal atoms, and they've each sent an electron out, and they're swimming around. So metals are going to be metallic atomic solids. And then the network covalent solids. There's not as many examples of this, but carbon does this. 2 different forms are diamond and graphite. Also the graphene that we learned about in that first slide, and silicon dioxide. So what's interesting about the crystal structures of covalent compounds is they're not just packed together in whatever thing is closest, right? They're constrained by the geometry of the hybrid orbitals that gives rise to those covalent bonds. So they do not have closest packed structures. They do have very high melting points. Okay, so these are the sorts of questions you should be able to answer. What type of atomic solid is AU? Metallic, because it's a metal, right? So some of the questions on tests seem too easy, and they actually just are easy, right? This one's a little trickier. Which solid would you expect to have the highest melting point? So let's think about what kind of things are holding these together. What's holding MgO together? Ionic bonds, right? This is an ionic solid. How about I2? Pardon me? Dispersion forces, yeah, intermolecular forces. So that's a molecular solid. And what kind of a solid would this be? An atomic solid, right? Because this isn't a molecule. I2 is a molecule, but this is an atom. So, we learned about dispersion forces and how they depend on size, right? So we can check on the periodic table and see, well, krypton has a mass, there's glare, about 84. Iodine has a mass of 127. and there's two of them, right? So this has a much higher mass than that one, but it doesn't really matter because the ionic bonds are much stronger than the covalent forces that are holding the molecular and atomic solids together. So you want to identify what kind of a thing is that, right? And we can go back to, what was it, chapter 3, where we learned to name things. Look at the first element. Is it a metal? Does it have some nonmetals with it? It's probably ionic.